All right, I'm going to give a shot to explaining what completing the square is, why we care about it, and how it works. So first of all, let's imagine that we have a kind of plain Jane parabola, quadratic, looks like this, of the form y equals ax squared plus bx plus c. You can see our a here is 1, our b is 0, and our c is 0. So right now this is plain old x squared. And this has kind of a familiar pattern. If you put in a 1, you get out a 1. If you put in a 2 for x, you get out a 4 for y. So we're squaring the input, right? And you can kind of see what happens when I change the a around, it changes the shape. We call it a stretch factor. When I change the b and the c around, it changes where the vertex is and kind of shifts it horizontally and vertically in the case of b, and just vertically in the case of c. But this isn't super intuitive. There's a way to figure out what's happening here. It's negative b over 2a will tell me the x value right here. I don't like that, though. I would like it if I could just find it in the equation, which we can do pretty easily using an equation of the form y equals x minus h squared plus k. You may have seen this before. This is vertex form of an equation. And if we put our h and our k as 0, then our vertex is 0, 0. If we put our h as 1, then our vertex becomes 1, 0. Put our k as 3, our vertex becomes 1, 3. So in this format, your vertex is h, k. You could write this as a plus and just remember that your h is backwards because it's happening before all the inputs. A lot of people, I like to write it this way because then I don't confuse myself by getting double negatives in there, and then I just remember that the vertex is backwards. But in any case, this form is a lot easier to use for getting an intuition about where your graph is going to be and what it looks like, because you know exactly where your vertex is and you can calculate your scale factor pretty easily after that. So if a was 2, then all the values are just 2 times bigger. So I'll pull up a table real fast. All right, so I've made a quick table here, and you can see that when a is 1, the values in the table kind of follow a squared pattern. So negative 1 squared is 1, negative 2 squared is 4, negative 3 squared is 9, and symmetrical on both sides. But when I make it times 2, we're just multiplying those values times 2. So it used to be 4 for this 2 value, but now it's going to be 8, right? And it used to be 9 for the input of 3. The output used to be 9, but now we're going to times by 2 and make it 18. So you can see with this vertex form, it's really, really easy to just take a normal parabola, x squared like this, and kind of watch where it goes as you shift it. If I move it over and I move it up, and then I scale times 2, I can do all those calculations pretty easily, kind of even in my head, without doing a whole lot of solving to find out where this sucker's going to land, right? So this is why vertex form is awesome. We love vertex form. But here's the thing, they give us standard form all the time because why? I don't know, they want to be irritating, I guess. Sometimes standard form is what you get. And there are actual standard form applications in physics, especially with position and velocity and acceleration and things like that. Those are some good applications. So standard form isn't totally worthless. It relates to the real world. But if I want to graph this sucker, then I want to look at it in vertex form. And the easiest way to get standard form to vertex form is by completing the square. So to start as concrete as we can, we're going to look at a standard form quadratic that we might want to graph or complete the square for whatever reason we're doing that, and then kind of build what that looks like in more complex cases and then in the general case. So first of all, just so that we're super clear on what we're saying, standard form of a quadratic is this sucker, ax squared plus bx plus c, where a is the coefficient of your x squared term, b is the coefficient of your linear term, and c is a constant, so it's just some number. And let's just pick one. It doesn't really matter what it is. Let's use x squared plus 4x minus 3, and let's see what it takes to complete the square with this thing. So I'm going to take this nice little equation. I'm going to pop it in my manipulatives tool here. This is Polypad, which is a free online resource for all sorts of manipulatives, including algebra tiles. So here's our original, what was it? Y equals 4x squared plus 4x minus 3. And I'm going to grab some different tiles here to model this. If you're not familiar with algebra tiles, we're really looking at rectangles, and the area of a rectangle is the length times the width. So this rectangle happens to also be a square, and the length is x and the width is x. So this is an x square tile. Likewise, you also have these x tiles where the length is still x, but now the width is going to be 1. So that width is 1. 1 times x is x. And then we also have our little 1 here that is length and width of 1. 1 times 1 is area 1. And some algebra tile sets will also have y lengths. So they can do y squared, which is different than x. And this tool is pretty fun because you can kind of change them separately. Anyway, we're not looking at that at the moment. We will split some tiles in half in a little bit, which is something you can't do with physical manipulatives very well. I don't suggest trying. I did try. It didn't work. Okay, so let's model this thing. We have an x squared. We've got 4 x's. And we have minus 3. So that's this thing, but negative and 3 of them. Cool. In factoring land, which is not the point of this video, you could factor this quadratic by making your algebra tiles into a rectangle and then finding the length and width of the entire rectangle. So, for example, if I wanted to factor this, I could say, okay, now I have made a rectangle. Unfortunately, these are negative ones, though, so we'd have to do some investigation into how the negatives work along. But the basic idea is this rectangle right here would have a length and width of x plus 3 and x plus 1. Again, just so we understand, this doesn't actually work. The negatives right here are not plus 3, they are minus 3, so you can't factor this thing this way. But getting the idea that a rectangle means that we have factored what we're looking at, I think is an important piece of this. Anyway, we don't just want a rectangle, we want a square. And I think you can see I'm not going to make a square like this because I don't have even height and width, so I am going to move one of my x's down. Now the question is, what goes in here to finish up my square? And you can see, I think, that it's going to be 4 1s, like this. Cool. And then we have this minus 3 that's still part of the equation that we haven't done something with. So let's talk about what we just did. We added 4 to the equation, and I'm going to make it orange so it matches the color here. We added 4. In order to compensate for this adding 4, we're also going to subtract 4. So this is just a fancy way of writing plus nothing. And we can add nothing to, it doesn't change the definition of this equation here. It's still equivalent. And so to model that, I'm going to show my plus 4 and also my minus 4, which is now here. And let's just line all these things up so we kind of see where all the pieces are. And then this is the plus 4 right here. This is my x squared, and my 4x is kind of bundled into this right here. So we'll put those all back together. And so we can see that this is still an equivalent equation. Now let's see what we got here. We took the square right here with side length x plus 2 and side length x plus 2. That's pretty cool. Has the same length and width. So this is x plus 2 squared in this piece right here. And then we still have over here some remaining negatives, and that's our minus 7, which is left over. And you can see that that 7 is the negative 3 and the negative 4 put together, the negative 4 that we used to compensate. So our new equation is y equals x plus 2 squared, quantity minus 7. And if you were to graph this thing, you could see that they are, in fact, equivalent, which is super cool. So, a couple things to watch out for when you're learning the technique of completing the square. You can always complete the square on any given quadratic. This is very possible. However, if your a term, so the coefficient of your x squared term, is not 1, you will need to make some modifications to your equation in order to use this method. So likewise, if your b term is not even, So you have 2x's here and 2x's here. It's a little harder to make a square without breaking some of the tiles in half. So let's take a look at what that might look like as an example. Just real quick, we'll do exactly the same thing. X squared plus 5x minus 2. What did I say? Minus 3 above. Doesn't matter really. And we'll start modeling this. So here's our x squared, here's our 5x's, and here is our minus 3. Oops, there we go. And what we want to do is turn this into a perfect square again to get it into vertex form. So we're going to take our x's and kind of move them around. And you'll notice we have a problem. This x doesn't fit. It needs to be split between the two sides, which we can actually do in this program, so that's cool. But now we have an x over 2, and that's kind of ugly. So just so that we're understanding what length we've made, this is now x plus 1, plus 1 plus 1 plus a half, which is really ugly. So this is x plus 2.5, right? And this is x plus 2.5. And now to put our 1's in there, just to kind of make this match up, we have the same set of 4 going on here, but we need some pieces. So we're going to take this, we're going to split it horizontally and put some halves in. You can see how this gets a little unwieldy pretty quickly. Oops. It works. It always works. And then, of course, there's this little tiny square left over. It's a half times a half. So what is that going to be? Well, 1/4. And now we're getting kind of ridiculous. This is a little bit crazy. How much did we actually add here? We've got our 4, and then each of these halves are 1. So that's 5, 6, and 1/4. We added 6 and 1/4. So our complete square here would be, we added 6 and 1/4 in orange. And to compensate for that, we also need to subtract 6 and 1/4. If you were showing this as a completing the square, just algebraic manipulation, I would take that equation and I would rewrite it as x squared plus 5x plus 6.25. And then I would remove the negatives together, the things that are left over. So that's minus 9.25. And then we can do our complete square here. We know that this thing right here is what we modeled up here. It's a perfect square. And it's going to be x plus 2.5 squared, and then minus 9.25. Okay, so we can kind of see it gets a little more complex when your middle term isn't even. And then there's one more piece of complexity to discuss, and that's when your coefficient a is not 1. So let's look at that real quick. I'll grab another color. Let's go teal. So let's do y equals 2x squared plus 4x plus 2. And since that factors kind of nicely, we can pull a 2 out of everything. I'll do this to make it a little more complex. Let's start modeling. So we have our 2x squareds, our 4x's, which I'm just going to start throwing on here. And as you can see here, that is not a square shape. This is not going to be a square shape in this current format. So what we need to do is take away that coefficient of 2 by dividing both sides by 2. And algebraically, it looks kind of like this. Where's my pen? We're dividing by 2, we're dividing by 2. And in the model, I forgot the plus 1 in my model here. There we go. In the model, what will happen if we are dividing everything by 2, I'm going to stack it kind of like this. You can kind of see these pieces right here will just cut in half, so I'm going to get rid of those. And then this also cuts in half, so that's our new model. This is what we have. And we'll compensate for the fact that we divided by 2 when we're done. If you want to make this equivalent right from the start, you could think of it as we're not just dividing both sides by 2. We're dividing everything by 2 and then compensating for that by remultiplying everything by 2. This thing means times 1. We can always multiply by 1. It doesn't change anything. A lot of students find it easier to divide both sides and then move that division back over by multiplying by 2 at the end. It's a little less complex to follow. It doesn't really matter which way you track it. The fact is that we're getting our coefficient of x squared down to a 1, so we can play with this. And now with the model, I think we can kind of see that we're almost there. We just need another half to make the perfect square. Algebraically, if you want to look at it this way, we're really looking at x squared plus 2x plus 1/2. and I'll just use a fraction here, is our kind of intermediate thing that we're modeling up here. What do I need in this little box to complete the square? Well, wouldn't it be nice if there was kind of a general way we could think about this? What do I need to do to figure out that the other thing I need is 1 more 1/2, so that this needs to say 1? We'll look at this in general terms in just a moment so that we can conclude what this generalizes to. But since we're here using the model, we're going to just add another 1/2, just like we have in the past. Here's another 1/2. And in order to compensate for that 1/2, we're subtracting 1/2 as well. This leads us to not add anything, and it is still equivalent. So presently, if we want our stuff to be correct, this is y over 2 equals that. Or you could have written it in parentheses if you want it to be a little more complex. That's fine. Doesn't matter either way. Okay, and we also know that if we do a little rearranging, our y over 2 has to equal x squared plus 2x plus 1/2 plus 1/2. I did this a little different than the last one, and I think I'll address that. We noted that we needed to add 1/2 total to get to the square, and in the last one that we did above, we said that the number I need is 4, and so we just added the 4. We could have compensated at the start. It doesn't matter how you do that. Here we're adding the 1/2. If we were to do it the other way, it would have looked like this instead. It would have been the plus 1 minus 1. And then we just move the 1 over. It doesn't really matter as long as the thing that is written right here is 1. So either way, I'm going to end up with a minus 1/2 outside of that and the 1 right here. And now we can complete the square. So y over 2 is in fact x plus 1 squared minus 1/2. And so we can see that on the model, x plus 1 squared, and then minus 1/2 is the leftovers. Okay, cool. So we've talked about some of the kind of complicated things that can happen when you are looking at completing the square. Now I really want to take this general. So let's take a look at exactly what's happening in terms of a general quadratic when we complete the square. So let's model this sucker the same way we did with the other ones and kind of see what the general conclusions are as a result of modeling. It's a little more difficult to do this with algebra tiles because the lengths and widths are going to confuse students. So I don't suggest, if you are going to talk about general form of complete the square, I don't suggest doing it with physical manipulatives that are going to imply that the lengths are certain things, and I'll show you what I mean. Let's take a perfect square here, and we're going to model our ax squared. I also am going to note that we just talked about why doing this with an a value that isn't 1 is difficult. So we're going to assume our a value is 1, and if not, we'll use our fancy math to be able to make that 1. So our a is just kind of not there. Where's my eraser? There we go, like that. So now we have our x squared, area x squared. Area equals x squared because the length is x squared and the width is x squared. Cool. Now let's take our bx term. This is where things get a little interesting. We don't know how many x's we have, so we have b of them. And that's a little hard to conceptualize. So let's just make one rectangle, and instead of making b rectangles, we're going to make that same rectangle have a length of x and the width of b. So you can imagine if these were length of 1 and length of x, this giant rectangle, or rather larger rectangle, would have a width of 2 together and length of x. Well, we don't know how many we have, so we're going to say this has a length of x and a width of b, because we don't know. And then that plus c part, which you saw just a minute ago, actually comes into play at the end. So we're going to leave it alone. We're just going to focus on these two terms. We can wiggle around with the constant and figure out where we get to. So let's take this bx rectangle right here. I'm going to rotate it and put it nicely. I guess I need 2 of them anyway. Oh no. What do? I can't make a square if this is here unless I have another one. So we're going to have to split that sucker in half. Boom. Kind of like that. And now let's just, so we're following, since I split length of x and length of b in half, this is really b over 2 right there. And then this little one is also b over 2. Let's make that bigger so you can see what I'm saying. This is also b over 2. So the length didn't change, but the width has been cut in half. And let's take those same things, that's the big one, and we're going to strap them onto our rectangle over here so that we can make a square. And we know this is going to make a square because of the length x being related to the other length in x squared. That shouldn't say x squared, though. I screwed that up. That should say x. There you go. So because this x is the same x as this one, this has to be a square. Now, what are we missing? What's the little chunk right there that's in the corner? Oh, man, I don't know what that is. Let's make it pink. What's it going to be? Well, we already know what the dimensions are. I'll make it even bigger so we can clearly see it. The dimension here is b over 2, and this dimension is x. We don't care about that. We already know. And this dimension is b over 2. So this little square at the bottom is going to have both sides as b over 2 and area b over 2 squared. Cool. All right, and then what do we do with the c? Well, the original formula we started with here was x squared plus bx plus c, and now we've added this b over 2 squared term. That was not there before. So we're going to add our b over 2 squared term, constant it is, and since we've added it, we're going to have to subtract it as well to compensate for the fact that we changed our equation. Now, this pink stuff here cancels itself out. This doesn't change the equivalence of the function, but it does allow us to do a very interesting thing. I'm going to rewrite this whole equation now as y equals x squared plus bx plus b over 2 squared. And then we have the rest of our equation, minus b over 2 squared, and then plus c in blue. And this is actually equivalent to the one on top, but we've written this in a very particular way. If you look at our model, the side length of x plus b over 2 is the same on each side, so our complete the square becomes x plus b over 2 squared. And now we have our things that we compensated with, minus b over 2 squared, and the plus c left over. So now we've generalized this for any quadratic where a is not equal to 1. It works nicely this way. You can generalize with a not equal to 1, but it's really complicated. It's a little more tough to follow. Anyway, and this is where the procedure becomes rote at some point where you're recognizing, okay, it's always going to be x plus b over 2 squared. And the term that I'm looking for is b over 2 squared. If we go back to the examples that we just did over here, let's look at this one, for example, at the start. Our b was 4. So the thing we're looking for is going to be b over 2. So 2 squared. And that would give us our square area of 4. And one more thing that Complete the Square does really well is it helps students who may have trouble with the complex manipulations of the quadratic formula to have another way to access solving quadratics by hand. Not that we shouldn't have our students be good at algebraic manipulations. I think it's particularly important for students who are college bound to have some of those skills, so that this is something that's important. But allowing access with more than one way to approach a problem, I think is always good to help our students get access to the mathematical concepts and learning. Anyway, when we are completing the square, we have this really interesting result that we can just kind of undo everything in a way that is not possible in standard form of an equation. And in particular, if you're looking for specific solutions. So let's keep solving this thing. Usually when we say solve, by the way, we're not equal to 0 or y anymore. We're now equal to 0. We're looking for the roots, and that's what the quadratic equation does. So let's make that distinction, and now let's solve it. I'm going to add 7 to both sides, and then I'm going to unsquare both sides. which means that we could get a positive or negative result. So plus or minus 7 equals x plus 2. And then subtract the 2 from both sides. And we get plus or minus 7 minus 2. Going to reality check myself here. Taking a look at the Wolfram alpha form, we can see our expanded form matches, and the roots are indeed plus or minus 7 minus 2. Very cool. Oh, and I suppose we should say equals x to make that answer complete. So this just offers another way for students to access solving quadratics. It does work with imaginary numbers and all those sorts of complex solutions. And since it's fun and you're probably a math teacher if you're watching this video, I think I will leave you the exercise of showing how this model right here relates to these solutions algebraically. So instead of solving this for y equals 0, take this thing right here, the original quadratic, set y equal to 0, and complete the square, and then see what happens and see what you get. Something really kind of interesting and even magical happens. And I'll leave the video there. See you later.